Okay, so you guys should be able to see the position versus time graphs worksheet. We worked on this the first problem yesterday, and we're just gonna finish talking about the other problems on worksheet number 3. So we have the first problem we did yesterday, and then we have another trial where the timer started their watch a little bit sooner. So if that happened, here we've got a situation where the position of the skater is a little bit closer because they started sooner, which implies that the motion of the skater actually started earlier than was measured in problem number 1. So in the second trial, the timer started their watch a little bit sooner and got the data that's represented in the table. First question says, pull out the position versus time graph for the skater. So first we need to label our axes. We need to go from 0 to 10 seconds. I'm pretty confident that's not going to fit across here. So we'll do what we did yesterday and put 2 seconds between each of these grid marks. I need to go up to 10 seconds. For my change in position, this time it goes up to 34. If I do 0, 4, 8, 12, 16, 20, 24, 28, 32, I don't quite get there. I'm going to put 5s there this time. So first one will be 0, second one will be 5 meters, 10 meters, 15, 20, 25, 30, 35, and that should be enough. So we're going to put these points on our graph then. At 0, we should be at 4 meters. At 2, should be at 10 meters. At 4, should be at 16 meters. At 6, 22. 8, 28. And at 10, 34. So there's what our data looks like this time. All right. So next, how far from the origin was the skater at 5 seconds? How do you know? Well, the easiest way to do this is just to read it off of our graph. So if we find 5 seconds and look up at our line, that's going to be between 15 and 20. So we can estimate. I would estimate based on my graph, it should be about 18 meters. I'm just going to write 18 meters, and I read it from the graph. That's okay. We could confirm this by finding the equation. That would be fine too, but it doesn't ask us specifically that we have to write the equation. So as long as your answer is consistent with the graph that you drew, then you're in good shape for this worksheet. Was the skater's speed constant? If so, what was it? We did a problem that was similar to this yesterday. Just like yesterday, we can say, yeah, I think that the skater's speed was constant. And I know that because the slope of the line on my position versus time graph was constant. So my slope was constant. In the first trial, the skater was farther along at 4 seconds than in the second trial. Does this mean that he was going faster? Well, we have to flip back and look at that data, right? So, oh, wait, we need to go back here and calculate our speed, right? Okay, so it says, so what was it? The way we're going to do that is our slope is equal to our speed. So our slope is going to be our speed, change in position divided by our change in time. Our change in position according to our data is that we started at 4 and ended up at 34. So we're going to do our final position. So our position final minus our position initial divided by final time minus initial time. This is our equation that we're going to always use for figuring out speed. Our final position was 34 meters. Our initial position was 4 meters. The time that passed was, the final time was 10 seconds, and the initial time was 0 seconds. So we have 30 meters per 10 seconds, or 3 meters per second. How does that compare to yesterday's problem? Yesterday's problem, we came up with 2 meters per second as our velocity. So our skater was actually going faster. So down here for part D, they were farther along at 4 seconds. Does it mean that they were going faster? Well, they were going faster. They were faster in problem number 2. But in problem number 2, they also started at a different position. In problem number 2, they started at 4 meters. In problem number 1, they started at 10. So when we're comparing those two positions, we have to keep that in mind too. So this is, in the first trial, the skater was farther along at 2 seconds than in the second. We know they were faster in problem number 2. We also know that in problem number 1, they started further ahead. And so because of those two things, we have to keep both of them in mind. But we know they were faster in problem number 2 because we calculated a faster speed. If we take a further look at those two problems, we notice that at 2 seconds, in the second problem, that's when this person reached 10 meters. So it took 2 seconds just to get to the point where the person started in problem number 1. So it probably wasn't the speed that got them there. It was probably because of where they started their motion. Okay, do you guys have any questions about that one? Okay, I don't see anything in the chat and I don't see anybody shaking their heads. So I'm just going to go ahead to the next problem. For problem number 3, something else is going to change. Now our skater is in a third trial and we have more data. We're going to need to change our data up or our graph up just a little bit. Now we have much more time to deal with. So if we want to get all the way to 16 seconds worth of data, can we do that along this with counting by 2? 0, 2, 4, 6, 8, 10, 12, 14, 16. We can, but only just. So 0, 2, 4, 6, 8, 10, 12, 14, 16, and then our object is going to travel just 8 meters. So these usually have 8 lines. I already get the sense just from these numbers that the skater isn't moving as quickly. So we start at 0, 0. It's also new. At 2 seconds, we are at 2 meters. At 4 seconds, we are at 4 meters. At 6 seconds, still at 4 meters. At 8 seconds, we should be at 3 meters. At 10 seconds, 2 meters. 12 seconds, 2 meters. 14 seconds, 5 meters. 16 seconds is 8 meters. So there are quite a few changes that took place through that motion. Our first step is to plot position versus time graph. What do we think is happening from 4 to 6 right here? Well, his position doesn't change, so our skater is stopped. We know that because the value for a position stays the same. What do we think is happening in the time interval from 6 to 10 seconds? How do we know? 6 to 10 is this period right there. And in that portion, our skater has changed direction and has changed speed. So skater And the direction that he's traveling now is in the negative direction. It's going back towards 0. And he's changed speed. So we can know he's changed speed because the slope here is much shallower than the slope here. In the first 4 seconds, our skater is traveling 2 meters each second. From 6 to 10, he's only traveling, let's see, 1 meter every 2 seconds. It's much slower. So much slower. Determine the skater's average velocity from 0 to 16 seconds. Now remember, velocity, we're just looking at 2 data points. We only care about where he started and where he ended up. So to figure out velocity, we're going to look at the displacement and the time. So velocity for those 2 time periods is going to be more like this purple line. So that's going to give us our average velocity. To calculate that, let's see, a way we can write this, you guys may have seen this in math. When you write the average for something, you just draw a bar over it. So I'm going to do V for velocity, put a bar over it for average velocity. And that's going to be my displacement divided by my change in time. My final position is 8 meters. My initial position was 0 meters. And the amount of time here was 16 seconds that passed. So 8 meters and 16 seconds gives us 1/2 meter per second average velocity. Now, their average speed is going to be different because with speed, we have to look at path length. So to do path length, we're going to add up all the distances here that are in orange. So the path length from 0 to 4 seconds is going to be a total of 4 meters. So we travel 4 meters across that part. Up here, 0 meters. From 6 seconds to 10 seconds, we're going to travel from 4 to 2. So that's another 2 meters. And when we're calculating distance for speed, these don't have a sign. We don't use signs with speed. And then the last, let's see, we have 0 meters, and the last leg where there's a difference goes from 2 to 8. So that's going to be a 6 meter total. So we're going to add all those together. We've got the zeros, we can decide if we want to use those or not. But to figure out speed is going to be our displacement, our distance divided by our change in time. And that distance is going to be 4 meters plus 0 meters plus 2 meters plus 0 meters plus 6 meters, all those little legs from up here, divided by the total amount of time that's passed. And again, that's 16 seconds. So when I add these together, 4 plus 0 is 4, plus 2 is 6, plus 0 is 6, plus 6 is 12. So I've got 12 meters over 16 seconds. Let's see, if we found the least common multiple of that, that would be 3/4. So that's going to be 0.75 meters per second for speed. So the speed is actually faster than the velocity. This is equivalent to 0.5 meters per second. So our speed is actually faster than our velocity. And the reason that happens is because this object traveled some distance backwards in here. And that's what made the difference, is there was some repeated travel in here. So our next question. In what situation might speed be a better measure of motion than average velocity? Did you guys have any thoughts about that you wanted to share? Do we have any track athletes out there? I think we do. So consider if you're going to run a track, right? If you're going to run a race where you have to do a full lap on a track, you're going to have a start line and you're going to go all the way around, right? And then come back to that starting point. If you're calculating velocity, your velocity should be 0, right? Because your race is going to start and end on the same line. Maybe if you go all the way around. I wasn't a track athlete. I recognize that there are some races where you don't start and stop on the same line. But if you're going to say, I'm going to go around the track one time, and your start and end point is the same, then that would mean your velocity is 0. And so for a track, you don't want to do velocity. You want to look at your speed because you want to include the distance around the track that you ran. So if your start and end point is the same, you don't want to use velocity. You want to use speed, because then you care about the distance that you went around that track. What about this? In what situation might average velocity be a better measure of motion than average speed? You guys have any ideas about that one? I personally find this one a little bit trickier to think through. But, it might be the flip side of this. If you are going to do something where you're in a straight line, they should be the same, right? So straight lines will be the same. And if you and if you're going in a straight line, you may prefer velocity because that tells you something about direction. If you've got two objects that are going in separate directions but at the same speed, velocity will be able to determine the differences between those. So those are some times that might be a nice thing to do. You guys have any questions about that one? No questions? Okay. So on the back, there's a ranking task. I think this is the first one that you guys did, that you guys have done, the first ranking task. So the way that I always approach these is I try to calculate things first. This one is going to ask us to graph the greatest average velocity and then the greatest average speed. So I'm going to change up my colors a little bit here. Most of these are actually going to have the same velocity or speed because most of these things are straight lines. So A, B, C, D, E. And all of those, the magnitude of the velocity is going to be the same as the speed, but the directions are different. And so E has a negative slope, so E is going to have a negative velocity, but still a positive speed because speed's always positive. F is going to be a little bit different because when we're looking at average velocity, we only care about the beginning and the end. So we're only going to care about those. All right, so this first one, we already have that the velocity is 0 meters per second because we've got a line that has a slope that equals 0. Same thing is going to be true for B. Our velocity is going to be 0 meters per second. If we're trying to calculate speed, we're going to see the same thing because there's no change in position. So I'm going to write speed is 0 meters per second. Here, speed, 0 meters per second. All right, C. C travels 10 meters in 10 seconds. So our velocity for C is going to be 1 meter per second. And it's in the positive direction. So it's going to be positive 1 meter per second. For speed, it's going to be the same. The distance traveled is still 10 meters in 10 seconds. So this is going to be 1 meter per second. It's positive. Speed's always positive. For D, D tries to trick you a little bit by putting the beginning not at 0, but at 3. So here, we figure out our velocity. We're traveling 7 meters in 10 seconds. So this one's got a velocity of 0.7 meters per second, and that's positive. And the speed is going to be the same, 0.7 meters per second. E is going to have a negative slope because we're going to start from our final position, which is 0, and subtract from it 15. So our total displacement is going to be minus 15 meters, but the distance traveled is still 15 meters. So when we're looking at displacement, it's a negative value. When we're looking at distance, it's still a positive value. So our velocity is going to be minus 15 meters over 10 seconds, so minus 1.5 meters per second, where our speed is going to be distance, 15 meters over 10 seconds. So speed is going to be positive 1.5 meters per second. Lastly, F, our velocity for F, we're going to travel 5 meters in 10 seconds. So 5 meters, 10 seconds is 0.5 meters per second. You guys may have noticed that I'm writing these all as decimals. I do that because they're easier to compare to each other. So I know that in math class, you guys learn things like fractions are more precise sometimes, and that's true. But it's more challenging to compare them to each other. And so in physics, totally expected that you're just going to switch these over to decimals. Now, our speed is going to be our total distance traveled divided by the time. The time doesn't change, it's still 10 seconds. But the first leg here is 10 meters, and the second leg is another 5 meters. So here, for speed, our object has traveled 15 meters in 10 seconds. So this should be 1.5 meters per second. So these two are very, very different values. Now, to rank them. What I'm going to do first is rank these. So I need to go most positive to most negative. So I'm going to find the biggest one that's positive, right? I've got a couple of zeros. I have a +1, plus 0.7, a minus 1.5, and a 0.5. The 1 is going to be the biggest one. So I'm going to put a C here. The next is D with 0.7. And if another way to kind of check these is just write them down here. I have one that's 0.5. And then I have two that are equal, that are 0. Now, some students don't like doing ranking tasks if two of them have the same values because they get a little bit wound up on which one should go first. It doesn't matter. You could write AB, you could write BA. If you want to be extra super clear, you can write an equal sign in between them to show me that you know that they're equivalent. But generally, it's plenty just to write them there. Your 0, my last one is going to be E. E has a negative 1.5 meters per second velocity. So there we go. C, D, F, A and B are equal, and then E. Explain my reasoning. See math above. I've told you guys, math works as reasoning in physics class. You don't have to write an essay there that explains to me how you know how to do that if you're showing me your work. Okay, so at average speed down at the bottom, this one's going to be different. I did it in a different color. That's one way I like to use extra colors. I calculated all of my speeds up here, and I'm going to start from the greatest to the least. Turns out I've got two that have a value of 1.5, E and F. So I'm going to write E and F first. 1.5, 1.5. My next one is C, which has got a velocity of 1.0 meters per second. D is 0.7 meters per second. A and B are still both 0 because neither of them moved. So A and B. And just so that I'm extra clear, I'm going to put an equal sign there. I'm going to put an equal sign over here too. So those two are equal. And so, if I was grading this as a quiz or a test item, I would have this written so that you could have either E or F in either of those positions and A or B in these positions. So there's actually 4 different ways you could write this and be correct. Explain your reasoning. See math above. All right, do you guys have any questions about those rankings? All right, it's 9:30, which means class time is up, and I don't have an assignment for you guys because it's a beautiful day, and I'm hoping that you guys will all take advantage of it. So I hope that you all have a wonderful afternoon, and I'll see you tomorrow. I hope. My daughter's home sick today, so I'll see you tomorrow.